So hello dear students, let us start with unit number 3 that is related with the stability of the control system, right? So now in unit number 2 we have seen the transient response of the system as well as steady state error of the system, right? Now let us check whether the system is stable or not, right? Stable or not, where we will check the system whenever the which response you are interested in. You are interested in the steady state response, right? So I will first of all give the outline. In this unit, what we will do, we will see first of all what are the prerequisites of the stability. Then in second part we will see what is the concept of stability, and then by using the transfer function how to determine the stability of the system. So for determining the stability of the system, we are having basically two methods, right? One is RH criteria and second is your root locus, right? So in brief, in this unit we will cover all these topics, right? So let us start directly with the prerequisites, right? So now see here, what is your transfer function? Transfer function is nothing but Laplace transform of output by Laplace transform of input with zero initial conditions, right? And as we know that this transfer function is nothing but a polynomial function divided by polynomial function, right? So let us say there is a numerator polynomial and there is a denominator polynomial, okay? So now how to find the roots of the numerator polynomial? So I will just equate the numerator polynomial is equal to 0, and then this a raised to n s raised to n plus a n s raised to n plus a n minus 1 s raised to n minus 1 and so on. It will go up to a n s plus a0 constant, right? So it is a polynomial equation, simple in terms of s, okay? So once we have this polynomial equation, we can definitely find the roots of the polynomial equation. For example, your quadratic equation is the polynomial equation. So what we can do, we can find the roots of the quadratic equation, right? So similarly, we can find the roots of this n degree polynomial equation. So how many roots will be there? There will be n roots, okay? So let us say that this is kn, some constant into s minus z1, s minus z2 and so on s minus zn. So how many roots are there? So there are total z1, z2, z3 up to zn. So there are n roots of the numerator polynomial, and the n roots of the numerator polynomial are called as zeros, right? So this is the terminology which you need to keep in mind. Zeros are nothing but the roots of the numerator polynomial. Similarly, we are having the denominator polynomial function, and it is represented by bn s raised to n plus bn minus 1 s raised to n minus 1, so on b1s plus b0 is equal to 0, right? So if we find the roots of this denominator polynomial, it will be s minus p1, s minus p2 and so on s minus pn is equal to 0. So how many roots we get? We get p1, p2 up to pn. So in total we get n roots of the denominator polynomial. So this roots of the denominator polynomial are called as poles, right? So are you clear that what are zeros and what are poles? So zeros are nothing but the values which if you substitute in the transfer function, then the transfer function will become 0, right? So or numerator will become 0, and whenever denominator is 0, that values when you put in the transfer function, when the denominator of the polynomial transfer function will become 0, that are called as your poles, right? So basically all this stability concept depends on the poles, right? Now this is one part, right? So I hope that zeros and poles it is clear to you. Now let us deal with second part, right? So what is your second part? Second part deals with your S plane, right? Second part deals with your S plane. So okay, I'll just yeah. So second part deals with your S plane. Now what is S plane? S plane is nothing but your sigma plus j omega, right? So sigma is the real part and j omega is the imaginary part. So S is a complex number, right? So if I want to plot the complex number, I will use Argand's diagram, right? So here Argand's diagram, I will take a real part on x-axis, imaginary part on y-axis. So this is your RE of S means what? Real part of your S. This is imaginary part of your S. So this is sigma plus j omega. Sigma, here it will be minus j omega, and here it will be minus sigma, of course. So anyway, if you want to plot, right, the value of S, so you will use this S plane, right? For example, S is equal to P1. So S is equal to P1. If you get the value of S as 2 plus 3j, So it will be where it will be, so it will be plus 2 plus 3j, so it will be in first quadrant, right? So like that you can plot the value of S, right? For example, how many poles are there? There let us say if it is a quadratic equation, in the denominator there will be how many poles? 2 poles, right? So that 2 poles you can plot on this S plane by using the values, right? So let us say that one of the pole is 3 plus 2j and second is 3 minus 2j. So where will the pole will be there? It will be plus 3 and plus 2j, right? So 3 plus 2j somewhere here in the first quadrant and 3 minus 2j somewhere here in the fourth quadrant, right? So this is the S plane, and we can plot the values of, or we can plot the poles as well as zeros on the S plane, right? So henceforward I will say that okay, S plane means what? This plane, right? Argand's diagram, S is a complex number. So yes, so this is the prerequisite of this chapter. Now let us start with the concept of stability, right? Okay, so basically what is a stable system? Now see, stability, is it important? Yes. So for any system, the stability is very important requirement, as well as we can find out the important characteristics of the system by using the stability concept, right? So first of all, let us understand what is the stability, right? What the stable system is. Okay. In previous chapter we have seen that yes, we have seen stable, then we have seen damped response, undamped response, right? Then critically damped response, and so on. So let us see what the stable system is, right? So what the stable system is, this is BIBO system, right? Means what? Bounded input, bounded output. Means for a system, if you are giving bounded input, then your output should be bounded or it should be controllable, right? So let us take again the traditional example of the fan. You are giving bounded input, right? Means what? You are giving 250 volts constant input, right? So for 250 or 230 volts constant input, the output is constant, that is 1000 RPM, right? So you are having the bounded input, you are having the bounded output, hence that system is called as your stable system, right? Second point is if we are not giving the input, right? If we are taking out the input, suddenly the fan is on, and if I switch off the supply, means what? I am taking out the input, right? Then output tends to be 0. After some time, the revolution of the fans will boil down to 0. So for stable system, this is the necessary condition, that if you remove the supply, output should be 0 after some time. And then roots of this system, or you can say that poles of this system. Roots means wherever I am saying roots, I will say the denominator roots, that is poles. So poles should lie in the left hand of the S plane, right? So this I can explain you by using this diagram, right? So for a bounded input, right? What is input in unit step? This dotted line is your input, right? So for a bounded input, your response should be bounded. Means what? Let us say this is undamped response, which always we want. So what happens, after some time, right? The output is bounded. Means what? The output is stable, right? So for the bounded input, for the stable system, output must be bounded, right? Now location of roots for this stable system is always, it will lie on the left hand side of the S plane. Left hand side of the S plane means what? If we divide this plane by using this y-axis, then the left hand of the y-axis is called as left hand plane, and right hand side of the y-axis is called as right hand plane. So whenever you are having the bounded input, bounded output system or stable system, the poles will always lie in the left hand side of the S plane, right? So this is your stable system. Okay, so for the stable system, we need to always consider that after some time your system will boil down and it will give the stable output, right? So we are not see, obviously there will be some error, right? 2%, 3%, 5%, whatever it is, right? But that error will be constant after some time, and you will get a constant output. Okay, so this is your stable system. Now let us deal with unstable system, right? So what is unstable system? For the bounded input, for the same input, output is unbounded, right? Means let us suppose you are giving a 250 volt supply to the fan, and unbounded means what? Initially the RPM of the fan is 100, then 200, then 300, then 400, 500, 600, 700. It is expected to means output is expected that it should become stable at 1000 RPM, but it will increase 800, 900, 1000 and means 1100, 1200, 1300, and it will continuously get continuously increasing, right? Means what? Your output is not bounded now. Okay, so for the bounded input, output is not at all bounded, right? And once input is given, and if you remove it, right, or once input is given, output goes on increasing, right? It will not means we don't have the designer of the system will not have any control on the output once input is given. And roots, obviously the roots or poles of the transfer function will lie on the right hand side of the S plane, right? So let us see it diagrammatically. So see, this is your for bounded input, this is your dotted line is your input, right? So for the bounded input, your system will give the unbounded output signal, right? If you observe here, the signal is increasing, right? If you see the peaks of this sine wave, then this is let us say 1000, 1100, 1200, 1300, and it will go on increasing, right? So this is your unbounded output. For the bounded input, you will get the unbounded output, right? Okay. And similarly, the poles will lie on the right hand side of the S plane. So this is regarding your